We now understand that an atom will take atomic orbitals and hybridize them to generate the hybrid orbitals necessary for covalent bonding. Let's look at some of the different ways these atomic orbitals can hybridize. Looking at BeCl2, the beryllium atom has 2 electron domains, since it has just the 2 covalent bonds and no lone pairs. In order to accommodate these 2 electron domains, it will need to hybridize 2 atomic orbitals. So it will take its 2s orbital and one 2p orbital and hybridize them to form 2 sp hybrid orbitals. These will be equal in shape and energy, and they will have a shape that resembles a combination of the s and p orbitals. These hybrid orbitals will be arranged 180 degrees apart in a linear fashion, and each of them can accommodate the 2 electrons necessary to form a covalent bond. The bonds will occur when the sp orbitals overlap with orbitals from the chlorine atoms. Let's see this illustrated in an energy diagram. For an isolated beryllium atom, we can see the 2 valence electrons sitting in the 2s orbital, while the 2p orbitals are empty. But when it hybridizes the 2s and one of the 2p orbitals, we get 2 sp orbitals, which will have an energy that is in between the s and p orbitals, and it will therefore put 1 electron in each according to Hund's rule, so that it can form 2 covalent bonds. Any central atom with just 2 electron domains will exhibit sp hybridization. If there are 3 electron domains around an atom, like there are for boron in this molecule, there need to be 3 hybrid orbitals to accommodate them. So an atom will take an s orbital and 2 of its p orbitals to make 3 sp2 hybrid orbitals. These orbitals will then repel each other so as to generate a trigonal planar geometry. The boron atom will therefore exhibit sp2 hybridization and trigonal planar geometry. Once again, we can compare the orbital diagrams for an isolated boron atom with a full 2s orbital and one p orbital half full, and then for the hybridized boron with sp2 orbitals that are lower in energy than the p orbitals and equal to one another, which is why each one gets 1 of the 3 electrons. Any atom with 3 electron domains will use sp2 hybrid orbitals. With 4 electron domains, like the 4 bonds around carbon in a molecule of methane, we will need to combine 4 atomic orbitals, so that will be the s and all 3 p orbitals to get 4 identical sp3 hybrid orbitals. These will adopt the tetrahedral arrangement found in a molecule like methane. For the orbital diagram here, we can see that the s and all 3 p orbitals will be utilized to get the 4 hybrid orbitals, each of which will overlap with the 1s orbital from a hydrogen atom to make a CH bond. Larger molecules utilize this approach as well. If we look at ethane, which is C2H6, each carbon has 4 electron domains and thus will be sp3 hybridized, and so this molecule will resemble 2 connected tetrahedrons. Now we understand the hybridization of atoms with 2, 3, or 4 electron domains.